Hi class, we meet again in this video. I'm going to show you an example how to solve your ideal regenerative Rankine cycle in an open feed water heater. So let's read together this example here. You have a steam power plant operates off an ideal regenerative Rankine cycle. So this is the schematic diagram of your steam power plant. Steam enters the turbine at 6 megapascal and 450 degrees C. So if you can have a look at this schematic diagram, so you will see that you have a turbine here. So the steam enters the turbine at 6 megapascal. So inlet to your turbine, the pressure would be 6 megapascal, and the temperature of the steam is already at high temperature, which is 450 degrees C. And it's condensed in a condenser at 20 kilopascal. So this is your condenser, and the pressure is 20 kilopascal. The steam is extracted from the turbine at 0.4 megapascal. So you can see the outlet of your turbine, they have two outlets here. And 0.4 megapascal is extracted to be heated up in this open feed water heater over here. And it says that water leaves the feed water heater as a saturated liquid. So you need to show this schematic diagram on a TS diagram, and then afterwards you need to determine the network output per kilogram of steam and the thermal efficiency of the cycle. So how are we going to translate this schematic diagram into TS diagram? Alright, so let's sketch a TS diagram in here. So you have two working pressure. This is the condenser part. Sorry, three working pressure. Right? And you are going to have two pumps and only one turbine. So let's label this one as 1. Going out from your first pump is 2. This is your 3. This is 4. And then inlet to your turbine is 5. This one is 6. And finally, inlet to your condenser is 7. Alright. So the pressure of your turbine is 6 megapascal. And then your condenser is 20 kilopascal. And the one that's going to enter your open feed water heater is 0.4 megapascal. Okay, so you will see that this is your open feed water heater, right? So as you can see, the inlet to your turbine, and this is the outlet to your turbine. So at the outlet of your turbine, you are going to have two ways. One will be going to your open feed water heater with the fraction of y here, and the other one will continue to your condenser with the fraction of 1 minus y. So you can imagine, for example, you have a kettle, and inside your kettle is full of water, hot water, right? So some part is poured into this into a cup, and then the balance of it are going to be poured into another cup. Therefore, we need to figure out how much goes into cup A and how much goes into cup B, right? And thus, in this example, so you will need to find how many goes into the open feed water heater, which is represented as y, and how many are going into your condenser, which is 1 minus y. So how are you going to find the fraction that goes into your open feed water heater and the remaining that goes into your condenser? So this is taken from your notes, right? If I can simplify this thing on how to make you better understanding on how to find this fraction, right? So we are going to start from your energy balance. So this is your open feed water heater. and you have down here you have from state 2, and this one is from state 6, and this one going out here is your state 3. So all of this is happening at this point, right? So you have here, and then here, and goes out here. Okay, so let's do the energy balance equation inside your feed water heater. So let's say we're only considering about your mass, so it's going to be mH2 plus with your mH6 is equal to your mH3, right? So because this outlet is equal with this inlet, so let's say the portions of this outlet is 1, therefore 1 minus y, and this one is your y. As you can see in this schematic diagram, you have one inlet and you have 2 outlets, but the summation of this one is going to make a total of 1. Therefore, if we represent the total mass as 1, and this sum fraction goes into this, we represent it as y. Therefore, the remaining must be 1 minus y down here. Okay, so at the outlet of your turbine goes y fractions to this 0.4 megapascal, and the remaining is going to be into your condenser here. When you rearrange this equation with respect to this mass, so what you will get is, so we wanted to know what is the fraction of y actually, right? So we substitute into this equation and then we rearrange it, so it's going to have this y value. We can find the y value from this one, right? So it's the same as your notes here. So the derivation of this actually comes from the energy balance in your open feed water heater.